I'm Ryan. And how do you read an academic paper? Have you ever been in an argument with someone who says, do your research as a way to quickly stonewall you and end the debate? Then you, being the enterprising young scholar that you are, go to look into the issue further to resolutely beat your opponent to a pulp with the depth of your wisdom and academic skills, only to end up face to face with a real academic paper? Often it feels like you've landed in a foreign language class, only with graphs and numbers and all that messy bad stuff instead of umlauts, I guess. We academics don't really make it easy, do we? Today, we'll crack the code using a real paper, Nuamah and Ogorzalek's Close to Home, Place-Based Mobilization in Racialized Contexts. Grab a coffee, a highlighter, and let's decode this thing together. I'm a trained quantitative political scientist, so that's where my biases lie. That said, we're going to be talking about reading quantitative research here. Most empirical poli-sci articles follow the same structure. First you have an abstract, an introduction, a lit review, a theory, data and methods, analysis, this includes tables and figures, then the conclusion. Once you see that template, reading starts to speed up a little bit. Let's begin with the TLDR, quite literally. You read the title, read the abstract, and then the headings. There, you've already built an outline without reading a single paragraph. Next, hunt for the signposts, words like we test, hypothesis, and results show. Circle them, then jot down the big five: the question, the theory, the data, the method, and the key findings. Let's expand on those ideas a bit, using our sample article from the American Political Science Review. The abstract tells us the punchline: massive Chicago school closures mobilized black communities politically. Next, we should note that the modern political science scholarship is slightly fluid in how it uses headings and article structure. Often, the literature review, the theory, and the introduction are all combined together, as they kind of are in this article we have here. An introduction is a fairly self-explanatory thing. And the literature review does exactly that. It explains how the current scholarship speaks to the particular research area at hand. The intro of our sample article previews a place-based mobilization theory and the author's several hypotheses. But what's a theory? In political science, a theory is a concise story about how and why the political world works the way that it does. It identifies the key players, pinpoints the forces that connect them, for example, power, moneyed interests, norms and institutions, etc., 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 and sketches the causal chain that turns those forces into observable outcomes, like high voter turnout or a shift in foreign policy. A good theory is abstract enough to simplify the messy reality of politics, yet concrete enough to generate testable predictions or hypotheses that researchers can check against real-world evidence. In practice, theory is the scholar's flashlight. It guides which questions to ask, what data to gather, and how to interpret patterns we uncover, always with the understanding that new evidence can dim or redirect the flashlight's beam. My cat is wandering around here somewhere. Figure 1 of the APSR article is a simple flowchart of the theory. If you see a figure like this, or following your reading of the theory section of the paper, you should ask yourself what causal or correlational arrows are the authors drawing, and do you buy them? So we kinda understand a theory, but what's a hypothesis then? In political science, a hypothesis is a clear, testable, best guess derived from a broader theory, an if-then statement that stakes out a directional claim about how one thing, an independent variable, should influence another, a dependent variable. The companion null hypothesis simply says that nothing special is going on here. No systematic relationship, no difference, no significant effect. Researchers collect data to see whether the observed pattern is so incompatible with the null that we are willing to reject it in favor of the hypothesis. Basically saying something is, in fact, happening. Together, these paired statements illustrate the logical engine of empirical research. Pose a directional claim, pit it against the nothing to see here null, and let the evidence decide which story survives.
M-E-T-H-O-D, man. M-E-T-H-O-D, man. M-E-T-H-O-D, man.
Table 1 of the sample paper is a cheat sheet of every data set and variable used in the article. Many papers have tables like this, but not all. Let's pause here and translate some common jargon you might come across. A population is everyone you want to study or speak to in the paper, who the results apply to, in this case all Chicago precincts or CCES respondents. A sample, then, is the slice of that population that the researchers could actually observe. A parameter is a single number that describes a true but usually unobserved feature of the entire population, like the exact average age of every registered voter in the county. In the case of this paper, this is the true but unobservable effect of closures on turnout. I also want to pause here and take a tangent to note two increasingly common terms or research designs in political science research. First, we have the notion of an experimental design. While they don't use one in this paper, it's important to know what this means. An experimental design in political science is a research setup where the investigator deliberately manipulates a political stimulus, for example, the campaign message or a policy cue. They manipulate this for one group while holding everything else constant, then compare the outcome to an otherwise similar control group to isolate the effect of that interest, right? That changed effect. Nuamah and Ogorzalek use a kind of natural quasi-experiment using distance to close schools as different treatment groups. I'm really glossing over this here, but I want you to be aware that this concept exists, and you might find yourself Googling it if you don't quite understand a research design of a paper that employs one. Just be aware that this is a thing that exists out there. Within that broader concept of experiments, we have survey experiments, which are the most common type. A survey experiment does the same trick as a questionnaire. It takes different respondents and randomly shows alternative wording, scenarios, or information within the survey itself, so researchers can measure how those subtle changes shift opinions or intended behaviors. Again, we don't find one in this paper specifically, but the CCES employed in the paper gives individual survey data regardless. Let's break down the tables and figures of our sample paper. Figure 2 shows a map shading black population and dotting closure sites. Treat maps like storyboards. Darker shades equal higher concentration. I love a good map. You see a good map in a paper, it's probably a good paper. Figure 5 shows a heat map of turnout change and mayoral support. If you compare the left and right panels, you see that the turnout is up, but votes for Emanuel are down near the dots representing school closures. Figure 6 shows a scatter plot with a smoothed line. A rule of thumb is that if the confidence rhythm, those are the outer lines following the trend line, hugs the slope, that's the central trend line, the relationship is more or less solid. Wider bars mean there's a lot of error. Table 3 shows ordinary least squares, or OLS, regressions of voter turnout and mayoral vote share. Think of each column as a different outcome we care about. For example, change in turnout, change in vote for a candidate, the little triangle symbol is delta, which means change. And then think of each row as a possible explanation. For example, distance to a closed school, neighborhood, income, racial mix, or other items of interest. In mathematical terms, the rows are independent variables and the columns are dependent variables. The number in any cell, called a coefficient, is the estimated effect, how much the outcome is predicted to move if the predictor ticks up by 1 unit, whatever that might be, assuming the other variables are held steady. Within those regression tables, you'll see significant statistics. The little asterisks or stars flag how unlikely it would be to see an estimate that large just by random chance if the true effect or 0. Convention says that 1 star, that's a p-value of less than 0.1, could be noise. 2 stars, a p-value less than 0.05, is a fair bet, and 3 stars, that's a p-value less than 0.01, it's very hard to explain away as luck. No stars mean the relationship is insignificant, and you can usually disregard those results unless the author specifically point them out. Here's a key point. A p-value, which is what researchers want, does not prove a theory. It only tells us that the data would look weird if no relationship existed. These stars are linked to p-values. Let's illustrate this more clearly. Picture rolling a pair of dice 100 times and landing double sixes 30 times in a row. Your eyebrows would skyrocket. A p-value quantifies that eyebrow lift by the probability of seeing that data at least this extreme if the nothing is going on story of the null hypothesis were true. Convention flags a p-value less than 0.05 as notably odd, a p-value less than 0.01 as very odd. There's an important caveat here, though. A small p-value tells us the pattern is unlikely under the null, not that the alternative is automatically correct or important. I also want to note some common regression types used in papers other than OLS. We've already talked a little bit about ordinary least squares, or OLS, and OLS is great for outcomes that slide smoothly along a scale, like turnout percentages, for example. Generalized linear models, or GLM, often you'll see this referred to in terms like a logit or a probit regression, for instance. These step in when the outcome is a yes or a no, or otherwise has hard limits. For example, a binary dependent variable where it can assume only the values of 0 or 1, yes or no, or probabilities, or non-negative counts. To simplify, both GLM and OLS have the same goal. They want to draw the best fitting line showing the relationship between the independent and dependent variable, but GLM lets the line curve, so the math never predicts silly values like 112% voter turnout. All of that's nice, Ryan, you might say, but that's a lot of fluffy detail. How do you actually read a regression table? First, glance at the sign in front of the coefficient. Positive means the outcome rises, negative means it falls. In other words, a positive sign or no sign at all indicates a positive relationship between the independent and the dependent variables. A negative sign indicates a negative relationship between the independent and dependent variables. Next, eyeball the magnitude. Numbers farther from 0 matter more in real-world terms. Only then should you check the stars for statistical backup. A tiny but significant effect may be less interesting than a big, imprecise one. Remember, context is king. That's why we talk about value-robust theories so much in our research. Here are some bonus clues for looking at this research. Standard errors, those are the numbers in the parentheses, measure uncertainty. The wider or larger they are, the shakier the estimate is. The constant or intercept is the model's baseline prediction when every predictor equals 0. It's not always meaningful, but needed for the math. R squared, or pseudo R squared, tells us how much of the ups and downs in the outcome the whole model explains. It's helpful, but not a quality score on its own. To simplify, an R squared or a pseudo R squared explains how much of the variability in the dependent variable the model that we're using explains. I want to make a side note on correlation and causation. When two variables dance in step, test scores rise as study hours rise, or ice cream sales climb when temperatures soar in the summertime, we call that rhythm correlation. It says nothing about why they move together, only that they do. Some duets are meaningful, practiced, and proficient. Others are coincidental. Ice cream and pool drownings both spike in July because of the heat. Rule of thumb, treat correlation as a cue, not a conclusion. Causation, then, is the stronger claim that X produces Y, like flipping a light switch and lighting up a room. To argue causation, political scientists look for three pillars. 1. Association. They move together. 2. Timing. Cause happens before effect. And 3. No lurking third factors doing the real work. Experiments, natural shocks, or razor-sharp statistical tricks edge us closer, but even then we speak in likelihoods and not absolute proofs. You might read some paper that employs causal methods. These are rarer than the alternatives that speak in likelihoods, particularly in certain subfields of political science, like American politics. I've provided a lot of detail so far, and a lot of it isn't super necessary to understanding a paper, particularly if you, the viewer, are an undergraduate or just an interested non-academic. So let's outline 3 frames of mind to be in when reading an article, and how I think you should approach an article in each frame of mind. If you need to know the gist of a paper before a class, just speed read with a purpose. First, you read the title and the abstract for the headline. Second, read the opening and closing paragraphs of the introduction, and establish an answer to why should I care. Third, read the first and last paragraphs of the conclusion. Establish an answer to what did they find. And fourth, do a quick scan of every figure and table. In 10 minutes, you can jot 3 sentences. Big questions, methods, and the takeaway. And you should be able to walk into a discussion of the article somewhat prepared. If you need to critique a paper, linger where the trouble hides, data and methods. Ask, do the measures truly capture the concepts of the theory? Is the identification strategy, for example, the experiment, the measures, or the instruments used, tight enough to claim a strong relationship or even causality? Check the sample size, missing data, and any robustness or checks the author's claim to do. Note what's not accounted for in the theory or controlled for in the models. Those omissions often spark the sharpest questions. The third frame of mind is going to be the rarest, particularly if I think you're watching this video. If you need to replicate or build on a paper, you should obviously read the full paper and then head straight for the appendix, replication files, or data repository. Verify valuable coding, scrutinize model specs, pay special attention to footnotes that flag alternative specifications. They reveal the author's own worries and save you from reinventing the wheel. This third frame of mind, like I said, is the least common, and if you're watching this video, I doubt you'll want or need to do any of this, but it's still helpful to know that those resources exist. Here's a pro tip. Spend the lion's share of your reading minutes on the theory section, usually one golden paragraph that links X to Y, and the figure/table zones. Literature reviews and lengthy method sections can usually be skimmed. Reading discussions and conclusion sections in detail are important because these are where the authors usually put the main takeaways and results anyway. It's their mic drop, so to say, for the paper. If you want to know more about how to read social science research, I recommend the book Reading Statistics and Research by Schuyler W. Huck. It's a friendly walkthrough of academic papers, sampling, measurement, and inference that doubles as a field guide for spotting good and bad claims in the wild. This is a very old edition, but there is an updated edition, I think, coming up to the early 2010s. I'd also recommend the book Statistics for Non-Statisticians by Birger S. Madsen. Image somewhere here. It's a book with no heavy math that really breaks things down in an understandable way. And my final and strongest recommendation is that you read The Tao of Statistics by Dana K. Keller. It has these like Zen-style nuggets that explain virtually every stat term you'll need in political science without using any math whatsoever, and you can read it in an afternoon too. It's really good. Altogether, I want you to remember that papers are puzzles and not a fortress. With a clear map and a curious mindset and maybe one of those books in your back pocket, you can crack any study wide open. There's a list of links to these books cited in the video description below. In the next one, we're going to dive into our first substantive area of study, the separation of powers. Until next time. Do you have anything to say? Huh? He doesn't have anything to say.